Hi, everyone. So that's me. There's the hashtaggy thing if you want to tweet the questions for the discussion time, but just watch the talk and we'll talk after. This is the awesome team of people I get to work with every day over in the States. So basically, this talk starts at Scotland.js last year. I've been a JavaScript developer for a while now. I was speaking last year at Scotland.js, and somehow one of the talks triggered this question in my mind, like, how does JavaScript actually work? Like, I understand the language, but how does it actually work kind of under the hood? So I went to JavaScript, and I was like, what are you? And it kind of replied, like, I'm a single-threaded, non-blocking, asynchronous concurrent runtime. Oh, cool, right. So how do you work? I have a call stack, an event loop, a callback queue, and some other APIs and stuff. OK, I've never heard of those things before, really, and I'm a JavaScript developer. Crap, like, am I a complete imposter here? So, like, what are those things, JavaScript? And the documentation for this stuff is, like, not very easy to find. Like, code documentation, sure. Like, how the runtime works, harder. So I was like, there's this V8 thing, right? Chrome's, like, JavaScript engine. There must be some documentation about that. So I was like, hi, V8, do you have a call stack, an event loop, a callback queue, and some other APIs and stuff? And V8's like, not really. I've got a call stack and a heap. I don't know what those other things are. Crap. OK. So basically, 12 months pass. And I do some research. And basically, I now realize that this is how JavaScript works. And basically, if all you get out of this talk today is some understanding of these various pieces, then I've done my job. So very quickly, because I'm going to go through all of this stuff, the heap stack bit with JavaScript at the top left, that is the JavaScript runtime itself. That is like the implementation of ECMAScript. But for your browser to work, there's various other pieces. There's web APIs, like the DOM, AJAX, set timeout. There's this thing called the callback queue, and then there's the event loop, which you might have heard of before. And in a browser, these pieces all work together to basically give you what you kind of think of as JavaScript. So as I said, the engine V8 or the other ones in the other browsers, which the names don't come to mind, basically is entirely made up of two pieces. There's the heap, which is kind of boring. It's like memory allocation and management. You don't really have to think about very much. And then there's the call stack. And that's it inside V8. So as I said, the heap, not very interesting. Let's take a look at the call stack. So JavaScript is single-threaded, which means it has a single call stack, which means it can do one thing at a time. So for those of us like me who didn't do computer science, what is a call stack? So here's like a very simple bit of code, right? There's print square, a call to print square at the bottom. Print square calls square, which calls multiply. And the stack, or the call stack, is basically how the JavaScript runtime figures out what function am I currently like working through, and when I'm finished with that function, where do I return to? So a stack is just a data structure, and the only interesting things about a stack are that you can put things on top of it, and you can take things off the top of it, and that's it. You can't put things in the middle or anything else. So let's run this code. So we jump into the file, and you could think of like the file as being like a main function. So we're running the main function, so we push main onto the stack. A couple of function declarations, nothing very interesting. And then we get to this print square for call. Well, we're calling a function. So let's push that onto the stack. OK, so now we can look inside print square. And immediately inside print square, there's a call to square. So let's push square onto the stack. And square calls multiply, so we push multiply onto the stack. And now we just have multiply just takes A and multiplies it by B, and then returns. So in terms of thinking about the stack, the return keyword basically says, OK, take the current function call off the top of the stack and go to wherever you were, like the next position in the stack. So we return, we pop multiply off the stack. Now we've returned multiply, we can return from square, and now we're back into print square. So the squared line is now complete. We can now do a console.log, push that onto the stack, run console.log, pop that off the stack, print square is now complete, print square 4 is now complete, main is complete. That is a call stack. You have undoubtedly come across a call stack in the browser before. If you had code something like this, baz, which calls bar, which calls foo, which throws an exception, in Chrome DevTools you would see this, and I'm sure you recognize this nice red thing, which basically means you broke something. that is a printout of the call stack, right? Or it's called a stack trace, I guess, in the browser. But as you can see, we've got uncaught error oops, which was thrown by foo, which was thrown by bar, which was thrown by baz, which was thrown by some anonymous function. So that, again, like you've come across this before. Another place you might have heard this term, the call stack, is if you had some code like this. So we call foo, which calls foo, which calls foo, which calls foo, which calls foo, until we blow the stack. And that's basically the browser telling you that, you probably didn't mean to go like 16,000 functions deep before returning from one of them, so probably, instead of crashing your entire computer, we'll just throw an exception. So that's the call stack. That's kind of the fundamental piece inside V8. So what's this blocking term that you might have heard of before? There isn't really a strict definition between what is and isn't blocking. It kind of comes down to implementation. But basically, at some point, things are slow. So running a function call is quite fast, we hope. Hitting RAM, reasonably quick. If you're hitting disk, you're getting into things taking some time. If you're hitting the network, like an AJAX request, like that may never even complete, let alone taking a relatively enormous amount of time. So in this kind of call stack model, what happens if things are slow? So this isn't real JavaScript. Put away your thoughts of async and callbacks and stuff for now. Let's pretend that we had a synchronous call to a network, to a URL. So getSync here is going to go away and grab some JSON or something from foo.com, then bar.com, then quux.com. So if we run this code, like, OK, we make a call to getSync. And, oh, I guess we wait. And at some point, it completes. And now we can make the call to bar. And we wait. And maybe this one never completes. Who knows? If it does, we can now finally call quux. And then foo bar quux. So why is this actually a problem? Like, that's kind of how a single-threaded other programming languages work, like Ruby or something. Will just block when you make a network request unless you start using threads. So the reason this is a problem is because in a browser, you fundamentally have to do more than one thing at a time. You can't just punt and say, oh, it's OK if we're a little bit slow. So as an example, here is this code running in a browser. It's simulated with basically a very, very big while loop behind each of these getSync calls. So on this web page, this code isn't running right now, but I can open an alert. I can open a tab with Google in it. I can just use the browser like I would use the browser until I run this code. I can't now click on anything. I can't open a tab. The button hasn't even rendered the fact that the button was clicked. It's still in the down state because the browser's just got completely stuck, right? Until finally these AJAX requests, which are going off at the bottom, they complete, and then all hell breaks loose because the browser remembered what I did. It just couldn't actually do anything with that information because the call stack was blocked. So that's why blocking the call stack is a problem. So what's the solution? Basically, Node said, or no, the browser has said, OK, we're not going to worry about threads. Let's not solve this with threads. Let's do asynchronous callbacks. And if you've done JavaScript programming, you know that asynchronous callbacks can be pretty confusing, and you wonder why the hell they're in there. But basically, it's kind of a forcing function of the fact that you're building something concurrent like a browser. So let's take this most stripped back async call we could possibly have. If you've seen code like this before, you know that the first thing we're going to do is run console.log hi. Then we have this set timeout call. Oh, excuse me. Then we have this set timeout call. And we're basically saying in this set timeout, here's a function, run it in 5,000 milliseconds. So we're going to skip over that, and we're going to log Scotland.js from the bottom. And then 5 seconds later, we'll log there. So that's like the most simple async call we could kind of demonstrate. So if we try and represent this in our stack model, like, how is this actually going to work? So we jump into main, console.log hi. Set timeout call is like a normal call in the stack. But now what happens? We know that the stack has to clear so that we can get to Scotland.js next. But if that stack clears, then where does this console.log there come from later on? So like, I guess set timeout clears, we log Scotland.js, we clear the stack, and then sort of magically 5 seconds later, this appears on the stack as if by like, where does that come from? So basically, what I told you was a little bit of a lie. So JavaScript itself, the JavaScript runtime is single-threaded. It can do a single thing at a time. But your browser, in the wider context, it can do multiple things at a time, and it hides a lot of that detail from you. So you can just think about JavaScript being this kind of single-threaded, one thing at a time model. And that basically brings us back to this. The web APIs on the right-hand side, these are the other pieces that are keeping track of other things happening. And they somehow communicate through this callback queue in the event loop and push stuff back onto your stack. So rather than me digging into that diagram, let's just walk through the code. So this is a kind of simplified representation on the right-hand side of that diagram. We've got the stack, we've got the web APIs, the task queue, and the event loop. So let's run this code. Jump into main, console.log hi, push that onto the stack, log it to the console, clear it from the stack. Now we get to the interesting bit, set timeout. We call set timeout with a callback and this 5,000 milliseconds. What happens? Well, what happens is we fire up effectively a thread, but it's kind of hidden from us by the browser. We fire up one of the web APIs, so in this case, the timer API. And we give it this callback and say, OK, here's the callback. You go off and do your thing, figure out how to count down for 5 seconds. I'm going to get back to business. So now that we've shipped that over to the web API, we can clear the stack. We can console.log Scotland.js, clear that from the stack, clear main, and then 5 seconds in the future, the web API is like, oh, hey, I'm done, and sticks it onto this thing called the task queue or the callback queue. And this is basically how the web APIs communicate with JavaScript land, because web APIs kind of live outside JavaScript land. And the event loop, while being the title of this talk, is actually stupidly simple. All the event loop does is says, if the stack is clear and there's something in the task queue, push the first thing on the queue onto the stack. That's literally all it can do. So in this situation right now, we can see the stack is clear because we've finished running through our main function. There is a callback on the task queue, so the event loop's like, OK, push that onto the stack. Now the stack's like, OK, I can run that code. I know how to run JavaScript. So it's like, OK, console.log there, clear that from the stack, and we're done. So that's the other pieces in that puzzle, and that shows you how this code goes from being in JavaScript land into the browser threads and then kind of back into JavaScript land. So possibly the most illuminating example of this is what happens when we do set timeout 0. So if you've seen set timeout 0 before, you've probably, like the first time you came across this, you're like, hang on, what? You would like to run this function in 0 time. OK, why wrap it in a set timeout call 0? Like, it just doesn't make sense intuitively. But now that we understand the event loop, we can kind of see how this works. So if you've run JavaScript before, you know that this will effectively do the same as the last example. We'll log hi, we'll skip over the there, we'll log Scotland.js, and then later on we'll log the there again. So if we run through it, it just works exactly the same way. Console.log hi, set timeout call, ship that to the web API, which immediately is like, oh, hey, I'm done. You wanted 0 seconds, what the heck? Sticks it onto the task queue. But note, the stack isn't clear yet. So the event loop's like, oh, OK, I'm just going to wait. The stack's not clear, so the rest of your code can carry on running. So we log the Scotland.js, clear the stack, push the callback onto the stack now that the stack is clear, log there, and we're done. So basically all asynchronous calls, so we've got timeouts, we've got AJAX requests, which is the XML HTTP request web API, and various DOM events. They all basically work in exactly the same way. As soon as you have this like indented function which you're shipping off to some web API, it's going to get shipped over and handled later by the event loop and the task queue. So really quickly, AJAX request, jump into main, console.log hi, make the AJAX request. So we're saying, hey, XML HTTP request API, here's a callback, here's a URL. Can you go and get that data for me? And when you're done, put the callback onto my task queue. So meanwhile, our JavaScript thread can continue running, console.log Scotland.js. And at some point, maybe, this XHR request completes and sticks the callback onto the task queue. If it doesn't complete and just errors or something, it doesn't actually bother our JavaScript thread anymore because it doesn't care until there's stuff on the queue. So assuming it completes, pushes the callback onto the queue, event loop picks it up, log the data, and we're done. OK, so final example. this is showing, basically, we have a really attractive button at the top right. And using something like jQuery, we're going to bind like a mouse down, a mouse up, and a click event, which is basically kind of 3 of the events that happen when you click on a button. So again, how does this work? Well, we effectively spin up the 3 web APIs. And this time, they're not timed APIs, right? They're responding to DOM events. So now that the stack is clear, every time I click on that button, we're going to ship the mouse up, down, the mouse up, and the click event. And say I click a bunch of times, we're just going to queue up all these events. And now the event loop's like, oh, crap, there's stuff in the queue. The stack's clear. OK, I'll push that onto the stack. Run console log down, clear. It's clear again. OK, and so on. So you can kind of see, in this example, you can see the sequential nature of how this works. If you have multiple web APIs doing things all at the same time, which you do in a browser, right? You've got AJAX requests completing, you're clicking on stuff, you're scrolling. These events just get queued and kind of work through one at a time. So JavaScript will run your callback until it's finished, and only then will it go and pick up the next thing in the queue. So 2 things to kind of take away from this. So one is obviously this model, getting this model into your head of what happens when I call an asynchronous function. And the other is this concept of blocking the event loop. So in the browser, we are given some ways of doing asynchronous code, right? The DOM stuff, timeouts, AJAX requests, we're explicitly given an asynchronous API that we can kind of handle that asynchronously. But we can still block the event loop. If you do while true on the stack's just going to sit there doing a while loop. And it's never, ever, ever going to finish. And so the event loop can't start picking up other things from your queue. Equally, if you start doing computationally intensive things, like image processing or something in the browser, that's hard work for JavaScript to do. And it's going to slow down that stack, basically, because you're going to be doing heaps of stuff before you ever finish, before you can pick up stuff. OK, so I've got 2 minutes left. So for question time, which we're going to take through in the other room, there's obviously a heap of implications in terms of getting this model in your head and understanding how it actually interacts when you're writing code. So kind of the first question is, well, what kinds of things are slow? What things might I put onto the stack which are going to be slow? So there's things like rendering, layouts, that kind of stuff. And how does paint or rendering actually work with the event loops? Kind of another question. So your browser only refreshes at 60 frames a second. But the event loop can tick much, much faster than that. So how does the event loop ticking interact with your browser actually repainting? And finally, I just want to do a really quick demo. This was going to be the talk, but it turned out not to be kind of flexible enough. So I basically built an entire tool that takes arbitrary JavaScript code, creates the visualizations you just saw, and then threw it away for the talk and recreated them all in Keynote. So. But this code is live at latentfit.com/loop. And basically, you can put in arbitrary JavaScript here, and it, using a schema, takes that code, instruments it like crazy, and then at runtime visualizes what it's doing. So in this example, we've got foo, which calls bar, which calls baz, which does a console.log, and then we use 3 set timeouts to kind of queue up those calls. So when we run it, well, we do 3 set timeout calls, queue those callbacks. First one gets picked up, gets run through the stack, and so on. So with this, we can really simply do silly examples. We can show the blowing the call stack and how that works. Basically, we call foo, we call foo, we call foo. So at the moment, this really just supports normal code and the set timeout API. I've done a proof of concept of working with DOM events and AJAX requests too. Basically, this takes the code, instruments the crap out of it, ships it to a web worker because you have to run stuff in another thread. A web worker is basically another thread that you can magically do, which I didn't dig into because that's a whole other level of complexity. So yeah, this is the thing that I'll demo in more detail through in question time if anyone's interested. And 20 seconds early, I think I'm done. Thanks, everyone.